we've developed quite a lot of theory now about the statistical physics and about the connection between entropy and the number of microstates and so on. So before we do any more, I wanted to give you a concrete example of this. And the simplest example of this is the paramagnet, which I introduced last week. Okay, so we're going to study this in some detail now. The statistical physics of the paramagnet. And this should hopefully give you some idea about how all these concepts connect together. Okay. So I already defined this paramagnet, but let me briefly refresh your memory. So I consider a block, dimension here is unimportant, of n spins, and each spin can either be up or it can be down. And we saw that for this system you can define a quantity called the magnetization, which is important. Okay, or before that I said, instead of up and down, I can label these spins as +1 or -1 in the following way. Si, I said it equal to +1 if the ith spin is up, and I set it to -1 if the ith spin is down, and then I define this quantity called the magnetization, which is just the average of these SIs. And I can write this then another way as the number of up spins minus the number of down spins divided by the total number of spins. Okay, we saw all this in the last time. Okay, what we're going to do differently this time is imagine that the paramagnet is in a magnetic field. Okay? So I put a magnetic field here, like this, external magnetic field, which I would give the symbol H. Okay? And because of the magnetic field, there's some energy difference between up spins and down spins. In particular, the spins try to point in the same direction as the field, which means that the up spin has a lower energy than the down spin. So let me continue over here. In an external magnetic field, H is the symbol usually given to external magnetic fields. B is the combined field. Okay, so in such a field, the spin has different energy, and in particular spin Si has energy called epsilon Si, which is minus some constant which I'll call mu, times the size of the field, times the direction of the spin. Okay? So you can see here if Si is +1, then it has a lower energy, and if Si is -1, it has a higher energy. Okay. So here, mu, this constant, is called the magnetic moment. Which relates how the energy depends upon the magnetic field. Now, if this is the energy of one spin, then I can find the energy of the whole system simply by summing over the spins. So the internal energy U is just equal the sum, I goes from 1 to n, of the energy of the ith spin, which is minus mu h times the sum I equals 1 to n Si. And then finally, if I use the definition of magnetization, which has this sum in it, you see that U is simply minus N, U is equal to minus N mu H times the magnetization. So a higher magnetization gives you a lower energy. Okay, so that's the first thing we need. We've connected the magnetization to the energy of the system. Okay. Next, we need to connect the magnetization to the number of microstates. Okay. And the number of microstates only depends upon M. And in particular, if there are N up spins and N down spins, then the number of ways of arranging them, which is the number of microstates, the number of arrangement is given by, this is a combinatorial problem we solved a few weeks ago, N factorial divided by N up factorial, N down factorial. So that's the number of possible ways of arranging them. So for example, if I have 2 up and 2 down, then I can arrange them in 6 different ways like this. For example. Okay, so this is the kind of problem we talked about before. Sorry, that's 6 different ways like this. But now we can solve N up and N down in terms of the magnetization N, because we have the following equations. M is equal to N up minus N down divided by N, and also N is equal to the total number of spins, which is N up plus N down. And it's straightforward to show that you can solve this N up and N down, and you find that N up is 1 plus M over 2 times N, and N down is 1 minus M over 2 times N. This is quite straightforward linear algebra, okay, to go from there to there. So therefore, if I put this into the formula for the number of arrangements, we get a formula for the number of microstates. This is Wm, which is simply N factorial divided by 1 plus M over 2N factorial, 1 minus M over 2N factorial. Okay. So this is our second important equation. We've worked out how the energy depends upon magnetization, and now we've worked out how the number of microstates depends upon magnetization. That's these 2 equations here. Okay, so these are important, so probably I should label them. Let's call this one number 1. And we'll call this one number 2. Okay, now using Boltzmann's definition, we can use this statement for the number of microstates to calculate the entropy. So entropy S is defined as Kb times the log of W. And if you see that if you take the log of W, you'll get log of factorials. So we need to make some approximation for this, and it's useful to use this result, which is known as Stirling's approximation. Which says the following: if I have a large number n, then the log n factorial is approximately equal to n times the log of n minus n. Okay. And we can use this result to simplify the formula for the entropy. Okay. This approximation, by the way, is quite useful, and it's quite easy to prove. So if you haven't seen it before, let me just quickly prove it. The idea is you relate a sum to an integral. This is a sum, and we can show that the right-hand side is equal to an integral. Okay, so let me just plot it first of all. If I plot the function log of n as a function of n, then you all know it looks something like this, right? It goes through 0 at the point 1, then 2, 3, 4, 5, and so on. So what's log of n factorial? Log of n factorial is the log of 1 times 2 times 3 all the way up to n. This is just definition of factorial. But for a log, you know that log of a times b is equal to log a plus log b. So therefore, I can write this as log 1 plus log 2 plus log 3 plus all the way up to log n. So I can rewrite this as a sum of logs. But what is this sum of logs? This sum of logs is simply, if I draw it on this graph, is simply the area if I make boxes like this. Okay. Right? The area of this box is log 5 plus log 4 plus log 3 plus log 2. Okay, and log 1 is 0, so it goes away. So I can approximate this as an integral from 1 to n of log n dn. Now this is really an approximation. This is exact, but this is an approximation. And from the picture you see the error we make is exactly equal to the area of these triangles here. Right? Because the integral is the black line, but the sum is the blue squares. Okay, so we do make some error. But if n is large, then these triangles are very small compared to the whole area under the curve. So if n is large, this is still a good approximation. Okay, and let me complete the proof on one slide, one piece of whiteboard here. You should know the integral of log n is just n log n minus n. Okay, from first year calculus class. Okay. So when I multiply this out, I just get n log n minus n plus 1, and then you can ignore 1 for large n. So that gives you the result. So that completes the proof of Stirling's approximation that log n factorial is approximately n log n minus n. Okay. Now, in fact, Stirling did do a bit better than this approximation, but this is the only result we need for what we're doing here. Okay, now let's apply Stirling's approximation to the formula we have for the number of microstates to calculate the entropy. Okay. Therefore, S is equal to KB times the log of w, but w itself has 3 factorial terms in, so we can write them separately. The first one is log of n factorial, then minus the log 1 plus m over 2n factorial, and minus the log 1 minus m over 2 times n factorial. Okay, let me use some different shaped brackets here to make it clear. Okay, so that's just using the formula we calculated, okay, which was number 2, so let me write that. Using the formula number 2. And now we can apply Stirling's approximation to each of these factorials, okay, because there were 3 factorials in general, and we can apply Stirling's approximation to each. So this will give us a lot of terms, but we'll see quickly they cancel. So now we apply Stirling's approximation. Now with Stirling's approximation we get the following. KB, okay? So the first one is n log n minus n. The next one is minus 1 plus m over 2n times the log 1 plus m over 2n plus 1 plus m over 2n. That's just from this term. And then finally from this term, we get minus 1 minus m over 2 n log 1 minus m over 2 n plus 1 minus m over 2 n. Okay. So as I said, we get lots of terms, but we'll see that many of these cancel now. Okay, so first of all, you see that these 3 terms cancel. This plus this is just a half n plus a half n, that's n, minus n is 0. Okay? So this and this and this all cancel. Okay? Next, I can split these logs into 2. Okay? So this is equal to so I have n log n minus 1 plus m over 2 times n log 1 plus m over 2. Okay, no, let me do it as 3 terms, okay. So I have log of 1 plus m plus the log of n minus the log 2. And then I have minus 1 minus m over 2n log 1 minus m plus log n minus log 2. And you see that now the log n terms also cancel, because I've got n log n, and then this plus this gives me n, and I've got another log n here. So the n log n terms here and here and here all cancel. So now I can write the final result down. S is equal to, let's take out a factor of n and kb and 2. Then all I've got inside is the logs 2's. This plus this gives me n, and this is 2, so I get 2 log 2 minus, and then here I've got 1 plus m log 1 plus m. And here I've got 1 minus m log of 1 minus m. And that's it. So this is our final expression for the entropy as a function of m. So let me write that explicitly. S is a function of m. Okay. And we can draw a graph what this looks like. Okay. And it takes values between -1 and 1, and it basically looks like a semicircle, something like this. Approximately like a semicircle, obviously not exactly like a semicircle. Something like this. That. Okay. In particular, entropy is a maximum in the center, where you can see if m is 0, this is 0, and here it's just equal to n kb log of 2. And then it goes down to 0 when m is equal to 1 or -1. Okay, well that's nice. That tells you how the entropy depends upon the temperature. Sorry, how the entropy depends upon the magnetization. But what we're interested in is the temperature. So now we can calculate this as well. And remember, we calculated this equation for the temperature. The temperature is 1 over T is equal to the derivative of S with respect to U when you do no work. And in this case, I can write this using the chain rule. This is ds by dm times the derivative dm by du when you do no work. And here, condition you do no work is simply that the field is a constant. Okay, so we need to calculate this. Now, equation 1 tells me that the magnetization is equal to minus u divided by n mu h. So therefore, dm by du at constant h is simply minus 1 over n mu h. That's the first thing. And then we have to calculate ds by dm. Okay. So therefore, let me write it down. Therefore, 1 over t is equal to, you see from Sm there, n's cancel, we've got kb on the top, so this becomes kb over 2 mu h times the derivative d by dm of that stuff there, log 2 minus 1 plus m log 1 plus m minus 1 minus m log 1 minus m. Okay, so this is what we have to calculate to find the temperature. Now this derivative is not particularly difficult to compute, so let's just do it. 1 over t is kb over 2 mu h times, well, this is a constant, so it disappears. If I differentiate this m and this m, then I get simply minus log 1 plus m plus log 1 minus m. That's from differentiating the m's outside the logs. And if I differentiate the m's inside the logs, then this one just gives me minus 1, and this one gives me plus 1, which cancel. These cancel, and therefore I can rearrange this to get that temperature is equal to 2 mu h over kb times the logarithm of 1 plus m divided by 1 minus m. hold on. There's a minus sign missing, right? This minus sign is gone, so there should be another minus sign here. Sorry. Right. And then this one cancels with that one to give you that. Okay, then it's right. Okay, so this is our formula for the temperature as a function of m. Okay, let's look what this looks like. Again, m can take values between -1 and 1. Okay. And it's like 1 over a funny log function. And if you plot this function, it ends up looking something like this. Okay, so this is temperature, how it depends as a function of m. Now, this makes some sense if you think about what this is saying. First of all, this point tells you that at t equals 0, m is equal to +1, which means it tells you that at t equals 0, all of the spins in the paramagnet are pointing in the same direction as the field, which is what you expect. Right? If I drop the temperature down to 0, then all of the spins should align with the field. And that's indeed what this point here is telling you. Right? At temperature equal to 0, m is equal to 1, that means all of the spins are up. Which is right. This is the behavior we should expect. Okay. If I go to some other point, let's say somewhere here, this tells me at some certain temperature t greater than 0, as I increase the temperature, the magnetization goes down. Okay. As I increase the temperature, the magnetization goes down. This means that my magnet starts to become less ordered. So as I increase the temperature, still most of the arrows are pointing up, but I now have a few which are pointing down. Okay. Something like this. Which again should fit with your intuition. If I start to increase the temperature, this will make the paramagnet more disordered. This means that it will start to have more up and down spins. And in particular, as the temperature goes to infinity, up this way, the magnetization goes to 0. This means that we have equal numbers of up and down. So as temperature goes to infinity, the number of up is equal to the number of down. So in other words, as the temperature goes to infinity, the external magnetic field has no effect. Okay? It's just completely randomly ordered. So hopefully these three things all fit with your intuition. At temperature 0, it's in the minimal energy state, which is an ordered state, that's right. As the temperature increases, it starts to get less ordered. That means that the up spins start to go down. And as temperature goes to infinity, the number of up spins and the number of down spins become the same. And the field has very little effect. So that's explained the positive m side of the graph. But we also have this rather peculiar negative m side of the graph, where here it predicts a temperature, and this is an absolute temperature on the Kelvin scale, of less than 0. Okay, so this is a peculiar thing. This system, according to Boltzmann's definition of temperature, can have a temperature less than 0 Kelvin. But I told you that 0 is the minimum temperature. So how do we make sense of this? Okay, so this example illustrates some important general points about statistical physics, so I just want to go through them one by one in some notes. And I'll also explain how we interpret this negative temperature region here. The first thing is that we got a graph for the entropy as a function of energy over there. And the shape of this graph is pretty general. So in general, S of u, we can substitute S of m in this case, is a concave function. Okay. If you don't know what a concave function is, it's quite a simple idea. Let me explain. It just means that it's going down. Okay. Well, it means that the second derivative is going down. It means the following. If I've got a function, which looks something like this, pick any 2 points on the function, the straight line between these points will lie everywhere under the function. That's the definition of concave. Pick any 2 points, say A and B. A, this one is B, and then the straight line from A to B will always be under the function. That's the definition. So if I take 2 points and I draw a straight line between them, then this straight line will always be underneath the function. Okay, and you can see indeed it is here. That's the general definition. If the function is differentiable, has a well-defined second derivative, then we can make this definition more simple. Simply the second derivative of the function is big and gets smaller, so it's negative, right? So you can, in most cases in physics, you can treat this as a definition, because in physics, most functions are differentiable, but more generally, this is the definition. Okay, so you can now see immediately what kind of curves are convex or not. If I have a curve like this, it is not convex. Sorry, it's not concave, because I can choose a point here and a point there, and then the straight line is sometimes below and sometimes above. So this one is not concave. If I have a function which looks like this one is also not concave, because in this case, the line always lies above the function, right? This one is actually called convex. But a function which looks like this, which is curving down, is concave. Okay. And in general, this is true. So for all of the functions f's of u we will calculate for all the different systems in this course, it's always a concave function. So it always has this sloped shape like this, like a hill. Okay, so that's about the entropy. Now let me start to explain this negative temperature region. The first point to note is that this is unusual. Most systems do not have a region like this with negative temperatures. So for most systems, you have that the derivative of S with respect to U is always greater than 0. In other words, temperature is always greater than 0. Now what does this mean? Remember, entropy is just the log of the number of microstates. So the fact that this derivative is positive means that increasing the energy increases the number of microstates. So if I increase the energy of the system, it increases the number of accessible microstates. Okay, and in general, this is the behavior we find. For most systems, if you increase the system's energy, you increase the number of microstates it can have. But for a few systems, and this paramagnet is one of them, there becomes a point where increasing the energy actually decreases the number of microstates you can have. But a few systems. Of regions where ds by du is actually less than 0, which means that temperature is less than 0. And remember, this 0 is measured in absolute units Kelvin, so therefore this is a kind of new phenomena. And we can interpret this in terms of number of microstates. If this is negative, then this means that increasing U decreases the number of microstates. Okay. Now for the paramagnet, this is kind of easy to understand why this is the case. Remember that the entropy is the number of microstates. If I start out in a state like this, where all the spins are up, then this has the minimum value of U. Okay? Now if I increase the energy of the system, then there are up and down are mixed up. Somewhere in between, we have lots of different possible arrangements. So we have a high value of the entropy. Here we've only got one choice. But if I increase the energy even more, then I force all of the arrows to be down. Okay? And in this case, I have a maximum energy. Okay? And at the maximum energy, again, there is no entropy. So for this paramagnet, the system starts off at lower entropy. As I increase temperature, so as I increase energy, it goes to a high entropy. But if I keep increasing energy, I start to force all of the arrows to go down. And therefore the entropy decreases. So this is the negative temperature region here. Okay. So critical to this existence of a negative temperature region is the fact that for the paramagnet, there is a maximum energy. Okay. There's an energy above which you can't go. Now, for most systems, this isn't true. If we consider the gas in a box, I can keep heating the gas hotter and hotter, and the energy just goes up and up and up. There's no limit to the amount of energy I can give those particles. But for the paramagnet, there is, and this is why you see this negative temperature effect. Okay, so let me say a few more things about negative temperatures then. The first thing which is a bit weird about it is, if you look here, remember that the energy of the system is minus m. So it's minus some constant times m. This means that the negative temperature region here actually has a higher value of energy. Right? So negative temperatures have higher energies. For the paramagnet, the negative temperature region has higher energy than the positive temperature region. So we usually think that increasing the energy will increase the temperature, but in this case, the negative temperatures actually have higher energy than the positive temperatures. That's another thing which is a bit strange. And in general, this is true. The negative temperatures are in some sense hotter than the positive temperatures. In general, T less than 0 is actually hotter than positive temperatures. And I can make this precise. If I put two systems together and one has a negative temperature and one has a positive temperature, then the heat will always flow from the system with negative temperature into the system with positive temperature. Connected. So if I've got one system which has a negative temperature and one system which has a positive temperature, then the heat will always flow from the negative temperature region to the positive temperature region. Heat will flow from system 1 to system 2. The opposite of what you might expect. It goes from the negative temperature to the positive temperature. And therefore, we can think of negative temperatures as actually being hotter than positive ones. Okay, so that's where I'll stop for today. So in this second half of the lecture, we've looked at this model of a paramagnet. The critical equation is this one, which relates the temperature to the magnetization within the paramagnet. And we've also seen this funny behavior of negative temperatures, which I've just talked about now. I will say that although negative temperatures are interesting, you very rarely see them. Because as soon as you connect a negative temperature system to a positive temperature system, the energy flows from the negative to the positive, and then here, the negative temperature becomes positive itself. So in the usual physical world, everything has a positive temperature. But theoretically, you can obtain negative temperatures. And indeed, recently there have been some experiments where they take magnetic systems and then by pulsing them with lasers, you can force them into a negative temperature state. So these negative temperatures do exist, they are real, but in most situations you never see them. So in most situations we're only interested in the positive temperature part. Okay, so that's where I'll stop now. On Thursday, we'll look at some more consequences of this equation here, relating to the temperature and the magnetization of the paramagnet. Okay, thank you. Okay, hi everybody. So today we're going to continue talking about the paramagnet, which is what we looked at last time. So let me quickly remind you what we saw about the paramagnet last time. So it's a very simple system, which is made up of spins, where each spin either points up or down, and the energy of each spin is decided solely by its interaction with an external magnetic field, which we call H. Okay? So that's the only interaction is between the spin and the magnetic field. The spins can only point up or down. Okay. Now, last time we calculated the entropy of this, which depends only upon the magnetization, and the formula we found was the following. Remember, entropy is defined as the Boltzmann constant times the log of the number of ways of arranging the system with that magnetization. So this turns out to be kBn over 2 times 2 log 2 minus 1 plus m log 1 plus m minus 1 minus m log 1 minus m. Okay. I mean, you've got all these formulas in your notes, so you don't necessarily have to write them again. But we can plot this then, a graph of entropy as a function of magnetization. And it looks something like this. It's entropy is highest when the magnetization is 0, and entropy goes to 0 when the magnetization goes to 1, something like this. Okay? And remember, in terms of energy, magnetization equals 1 is a low energy state, right? So this is low energy here, and this is high energy here. So opposite direction to the magnetization. Okay? We also calculated the temperature. Okay, so let me say. S is defined as Boltzmann constant times the log of the number of ways of arranging the system. The temperature is defined as, in statistical physics, 1 over T is equal to the derivative of entropy with respect to energy, okay, when you do no work. Okay. So in this case, that just means a constant field. Okay. And we found from this the temperature, which we also got last time. So if I write down the equation from the notes last time, the temperature of the system is equal to 2 mu h, that's just the interaction of a spin with the field, divided by the Boltzmann constant times the log of 1 plus m over 1 minus m. So this gives you the temperature as a function of magnetization, and again we can draw a graph, which I did last time. And if you draw a graph of this one, it looks something like this. So as you'd expect, remember this is low energy and this is high energy. So low energy states correspond to low temperature, high energy states correspond to high temperature. So what we're going to start by doing today is to take this formula for the temperature, and look at some more consequences of it. Okay, because there are some interesting things we can say about this result, which allows us to make some physical predictions. Okay. Now this is actually the content of the worksheet 5 question 1, which I gave you last time. Worksheet 5 question 1 is all about taking this formula and seeing some consequences. So I'm basically just going to work through that question on the worksheet now. Okay. So this next 20 minutes or so is going to be solving this question on the worksheet. Okay, the first part, A, simply says, take this formula and make m the subject. In other words, make this formula m equals something. Okay, now this is just math. It's just rearranging math, so I'll just do it quickly. First of all, we have that log 1 plus m over 1 minus m is equal to 2 mu h over kbt. Okay, now if I exponentiate this, I get that 1 plus m is equal to e to the 2 mu h over kbt times 1 minus m. That's just exponentiating and multiplying by 1 minus m. Okay, then I can group the terms in m together. So this means that m1 plus e to the 2 mu h over kbt is equal to e to the 2 mu h over kbt minus 1 from there. And then finally I divide to make n the subject. M is equal to e to the 2 mu h over kt minus 1 over e to the 2 mu h over kt plus 1. Okay, that's the result. The question asks you to write it in terms of a hyperbolic tangent function. So to do this, you just multiply top and bottom by e to the minus mu h over kbt, and this gives you e to the mu h over kbt minus e to the minus mu h over kbt divided by e to the mu h over kBt plus e to the minus mu h over kBt. Okay. If you can't read these things in the exponent, they're all the same. They're all mu h over kBt. Right, okay. So in conclusion, and this is exactly the hyperbolic tangent function, so we get the result that m is equal to hyperbolic tangent mu h over kb times t. Okay, so that's our first result. And we can draw a picture of this. It's basically just this picture turned on its side, but we can plot a picture now. This is the magnetization as a function of field for fixed temperature greater than 0. This is just a tangent function, and hopefully you know what the tangent function looks like. It takes values between -1 and 1, and is asymptotic to -1 as m goes to -infinity, then it goes up, and asymptotic to 1 as m goes to infinity. Okay. I can also draw a graph of how does the temperature depend upon magnetization. Okay. And then this is, as I said, just the inverse of what was written there. So it looks something like this. Again, it takes values between 1 and -1. Okay, and this is the picture for fixed field, again positive. Okay, so some interesting things we can note about these graphs. First of all, if h is equal to 0, then the magnetization is 0. This makes sense. This means that if there's no field, then the spins are just random. Half of them point up and half of them point down. If there's no field, the spins are just in random directions. As I increase the field up, more and more spins start to point up, which is what you'd expect. Right? So at temperature equals 0, the spins are all in random directions. As I increase the field, the strength of the field, a few more start to point up, and if I make the field very, very strong, then virtually all the spins point up in the same direction as the field. Okay? Now this is the kind of behavior you would expect from a paramagnet, so that's good. Okay? And I talked about this one in the last class. At low temperatures, the paramagnet is in the ground state, which is all the spins pointing in the same direction as the field. As I increase the temperature, the paramagnet becomes more disordered. You have more random sequence of spins, and as the temperature, this isn't right. Sorry, this is sorry. In both cases, I've got the axes wrong. That's why it doesn't make any sense. Okay, this is the magnetization. What am I doing? Yeah, this is the magnetization as a function of field. This is the magnetization as a function of temperature. Sorry. Okay, but what I was saying is correct. At temperature equals 0, the magnetization is 1. That means you're in the ground state. As the temperature goes to infinity, the magnetization tends to 0, which means that you're completely disordered. Okay, all right, that's now correct. Okay. Okay, part B is asking you to find the heat capacity, which is a quantity we're going to be very interested in the remaining of this course. And the heat capacity per spin I want to calculate this is defined as 1 over n times how much does the energy change as a function of temperature. Okay, so how much energy do I need to change the temperature by a fixed amount? Right? This is the definition of heat capacity. Okay, now so we have this equation. U, we had, is it equal to the magnetization times the energy per spin, which is minus n mu h times m. This is minus n mu h times tanh mu h over kBt. So this is an expression for the energy of the magnet. So to get the heat capacity, I just have to differentiate this at constant temperature. And if I divide by n, it just gets rid of that, right? Therefore, C is equal to, the n's cancel, so I get minus mu h times the derivative with respect to temperature, d by dt, of tanh mu h over kBt. Okay, that's derivative with respect to temperature, taking h as a constant. Okay, and the derivative rules for hyperbolic functions work more or less the same as they do for trigonometric functions. In particular, if I have d by dx of tanh x, then this is just 1 over cos, hyperbolic cos squared x, which is exactly the same as for trigonometrical functions, right? The derivative of tan is 1 over cos squared. Okay. So using that result, here we get 1 over cos squared, so we get minus mu h times 1 over cosh, this is usually spoken cosh squared mu h over kBt, multiplied by the derivative of what's inside here with respect to temperature, which will give you minus mu h over kBt squared. Okay. And you can combine this into a nice form. If you see the minuses cancel, this is simply equal to Boltzmann constant times mu h over kBt divided by cosh of the same thing all squared. So I can write the final result like that. Okay. If the temperature is very small, then this thing is very large, and cosh is an exponential, right? So this is enormous, and the heat capacity goes to 0, so you have an exponential decay down here. It then rises up and reaches some maximum point, but then if T becomes large, then this is approximately equal to 1, and therefore this goes like 1 over T squared. Okay? So then it goes down like 1 over T squared. So it looks something like that. So for low temperatures, you have an exponential decay because of the cosh function there. And for high temperatures, it goes something like 1 over T squared. Okay. We can give you some idea of approximately what this is like. The maximum is independent of choice of h and so on, or mu. It's always just about 0.4 times the Boltzmann constant. So that's the maximum heat capacity of a paramagnet per particle is about 0.4 times the Boltzmann constant. Okay? Okay? And the value down here, which it attains its maximum, is approximately 0.8 times mu h over kb. Now, the fact that the heat capacity has a maximum is unusual. If you look at most systems like gases and solids and so on, their heat capacity just tends to increase with temperature. So most systems, the heat capacity will just increase. But the paramagnet shows a maximum. This is unusual. And for this reason, it's called a Schottky anomaly. Schottky is the guy who first named it, I think. And an anomaly is something which is unusual, right? So the fact that it has a maximum is unusual, so it's called an anomaly, and it's named after Schottky. Okay, Schottky anomaly. This is given the symbol chi, and it's defined, well, in the units I use, as the magnetic moment times the derivative of the magnetization with respect to the field at constant temperature. Okay, now this magnetic susceptibility is a quantity which is very interesting to experimentalists. If you see what it says, if this thing is a large number, if the susceptibility is high, then a small change in the field will give you a big change in the magnetization. Okay? So if this number is high, small changes in the magnetic field make a big difference to the paramagnet. Okay? Therefore, we say the paramagnet is susceptible to changes in field, and that's why it's called susceptibility. Right? On the other hand, if this thing is very small, then it means you have to change the field a lot in order to change the magnetization. So if this thing is small, then you have to have a very large magnetic field to improve the magnetization of the paramagnet. Okay? So this is a measure of how easy the thing is to magnetize. Okay? If this number is big, it's very easy to magnetize the paramagnet. If this number is small, it's very hard to magnetize the paramagnet. Okay. And this is the formula for it. And because we know the magnetization, we can calculate this. So this is mu times d by dh, constant temperature of tanh mu h over kBt. And again, it's virtually the same as the heat capacity calculation, except now you're doing with respect to h rather than t. So this turns out to be mu over cosh squared mu h over kBt. That's the same. Multiply by the derivative with respect to h. That's mu over kBt. So our final answer, let me write it on a new bit of board. Final answer is that susceptibility is equal to mu squared, magnetic moment squared over kBt, times 1 over cosh squared mu h over kBt. So again, let's plot some graphs of what this thing looks like. Susceptibility as a function of field for fixed positive temperatures, and susceptibility as a function of temperatures for fixed positive fields. Okay, and if you plot these functions, you get graphs which look something like this. It has some maximum here, then it decreases. Okay? So the susceptibility of a paramagnet is maximum at zero field, and then it decreases as you increase the strength of the field. More interesting is the temperature, which looks something like this. This one again has some kind of maximum peak, and then goes down to zero. So again, we can understand this graph in a kind of intuitive way. When the temperature is zero, that means the paramagnet is in the ground state. Okay? When the temperature is zero, that means all the spins already point up. So changing the field, making it stronger, doesn't change very much, because you're already close to the ground state. Therefore, the susceptibility is low. Conversely, at high temperatures means the system is trying kind of random. Okay? So at high temperatures, you've got half the spins up, half the spins down, and increasing the field does not have a very large effect, okay? Because the temperature drives the system into this random configuration. Now, somewhere in between that, you have a maximum. You have a point where the susceptibility is the maximum, okay? Where it's most susceptible to changes in field. So that's what the results look like. In particular, and to relate this to some real experiments, in particular interest is the case when the field is zero. If the field is zero, then cosh of zero is just 1. So this term goes away. So the answer is just mu squared over kBt. Okay? And this result is known as Curie's law. It was discovered, I think, by Pierre Curie, the husband of Marie Curie. Okay. And he discovered this law experimentally. Okay? So he was looking at paramagnetic materials, and he found that if he measured their susceptibility, then the susceptibility went like 1 over T. It was inversely proportional to temperature. Okay? So this was first discovered experimentally, but now, using statistical mechanics, using statistical physics, we can prove why the susceptibility is proportional to 1 over T. Okay? So this is an experimental result, which later on was derived using theory, and this is the first result in this course where I show you how statistical physics can be used to derive experimental predictions. So this Curie's law was first discovered experimentally. Okay, there's one more interesting point I want to make about this. The fact that chi at h equals 0, okay, let me write it this way, is proportional to 1 over t. Okay? This means that you can use this as a thermometer. If I have a paramagnet and I measure its susceptibility, I know that that susceptibility is inversely proportional to temperature, and therefore by measuring its susceptibility, I can calculate the temperature. So paramagnets can, for this reason, be used as thermometers. Okay? And in fact, they are used as thermometers in various situations. So what you do is say, I know that at room temperature, the susceptibility is something, let's say 2 or whatever. If I then measure it again, and I find that the susceptibility has doubled, now 4, then I know the temperature is half. Okay? If I find the susceptibility goes up to 8, then I know the temperature is a quarter, and so on. Okay? So by measuring the susceptibility, I can compute the temperature, and therefore we can use this as a thermometer. And this thermometer is particularly useful at low temperatures. so these paramagnets are used as thermometers in low temperature devices, is particularly useful at low temperatures because it's inversely proportional to temperature. Okay, so the graph looks like this. At low temperatures, you get a big change in susceptibility for a small change in temperature, and therefore it's a very precise measuring device. Okay, the last thing I want to do today is show you a presentation. This is, again, looking at the paramagnet, but I've got a computer to run a simulation, so this is the handout, and I'll talk about this now. Okay, so what this is I wanted to show you how we can use these ideas from statistical mechanics to look at the interaction between two systems. You remember we talked about this last time, right? I take two systems and I join them together and then see how they interact. Okay. We can now consider a very simple example of this where both of these systems are paramagnets. Okay. And see how two paramagnets interact. Okay. So we have two paramagnets in a magnetic field. Their sizes are N1 and N2. I give these some numbers later. Now, because total energy is conserved, that means that the sum of the magnetization is fixed by the conservation of energy. In fact, that's not quite true. Okay. The magnetizations can change because this paramagnets can interact. But, okay, there's a mistake on this slide. What is constant is the N1, M1 plus N2, M2. This is a constant. Okay. So it's not N1 plus M2, it's this. Okay, sorry, that's a mistake on the slide. So let me make a note to change that. Okay, so the magnetizations can change, but the total number of upspins and the total number of downspins should be the same. Right? Should stay the same. So, how can the microstate change? Well, I suppose that the following thing is possible. If I have, in one paramagnet, here's a spin up, and in another paramagnet, here's a spin down, then they could choose to flip like this. Okay? So originally, paramagnet 1 has a spin up, paramagnet 2 has a spin down, and at some point in time, they can simultaneously flip. Right? This conserves the energy. Right? The energy of this paramagnet goes up, the energy of this paramagnet goes down, but total energy is conserved. Right? So we allow this spin flips like this to happen. Okay, finally, at the bottom of this slide, you can see a model of the two paramagnets. So I use blue arrows pointing up to denote up spins, red arrows denote down spins. Okay? And here's N1 and here's N2. Okay. Okay, so now in the second slide I give some numbers. I suppose that the first paramagnet is twice as long as the second. So the first paramagnet has 1,000 spins and the second paramagnet has 500 spins. Okay? And we assume that the first paramagnet is roughly half and half. Okay? So 520 point up, that's these red ones here. Oh no, yeah. No, sorry. 520 point up, that's the blue ones. Right? Blue ones point up. 520 point up and 480 point down. That's the first paramagnet here. In the second paramagnet, we assume it's in the ground state. The ground state means that all of the spins are pointing up. At the beginning, right? So we then run the simulation, so we allow the spins to flip in the way that I described. So what do some things look like? Well, we can use this formula for the entropy to calculate the probability distribution of the magnetization at equilibrium. Okay? The way we do this is as follows. So I told you that the probability of having energy U1 is proportional to the number of ways of arranging the first paramagnet with energy U1 times the number of ways of arranging the second paramagnet with energy U2. Right? So that's the probability, and of course, U1 is proportional to M1, and U2 is proportional to M2. So I can use this formula, and W is just the exponential of the entropy, which is this. Right? So I can use this formula to calculate the probability. And if you do that, then you see this graph here. And the reason I made this graph is to show you the thermodynamic limit. Okay? So the average of M is about 0.35. Okay? That means that about 2/3 of the spins are pointing up. And that's easy to understand because initially, in total, 2/3 of the spins point up. So after it's all became average, you'd expect 2/3 up in the first paramagnet and 2/3 up in the second paramagnet. Right? So that's why this is the maximum here. But what's interesting is I plotted it for 3 different values of N1. If N1 is just 100, then you get this yellow curve, which is very wide. Okay? So there's a wide range of probabilities. If N is 1,000, then you get this curve here, which is sharper. If N is 10,000, then you get an even sharper curve. Okay? Now this is the thermodynamic limit, which I mentioned in the last lecture, or maybe a week ago. We expect that as the number of particles becomes large, the probability distribution will become sharp. Okay? And therefore, the value of M1 becomes definite. And this is what I wanted to show you. Okay? So if N is small, then it's quite a wide distribution. But as N becomes large, it becomes sharp. In our case, we're at this case, right? M1 is 1,000. So that means we will have some width of possible values. So we expect M to take values between about 0.32 and about 0.4. This range of values. Okay? These are the graphs which I've drawn on the board. The entropy looks like this. You have high entropy at low magnetization and low entropy at high magnetization. Okay? And the temperature looks like this. Okay? Low temperature at high magnetization and high temperature at low magnetization. So, if I go back to the initial state, this second paramagnet, this one, starts off with temperature 0. Okay? Because it has magnetization 1, so it has temperature 0. So this one has temperature 0. The first paramagnet is about half and half, so that means magnetization is nearly 0, so it starts off at very high temperature. Okay? So when we join these two paramagnets together, the first one is at high temperature, and the second one is at low temperature. And you'd expect that the temperatures should become equal. Right? This is what you expect to happen. Okay, so now I show the simulation, and if you look up here, you can hopefully see that some red bits are turning blue, and some blue bits are turning red. These are the spin flips happening, right? So I got the computer to pick 800 spin flips, so it does this 800 times. And at the same time, I plot what's the magnetization of each paramagnet. This is the second paramagnet and the first paramagnet. And what's the temperature of each paramagnet. So I'll just let it run. Okay. So after 800 time steps, you end up with a situation where both of them look more or less the same. This in particular means that their temperatures have become more or less equal. So the first paramagnet started off at high temperature, the second paramagnet started off at low temperature, but at the end, the temperatures became equal. This is the right kind of behavior. Right? This is what we expect. And this means that their magnetizations become equal because temperature is a function of magnetization. That's one thing. Another thing you can see is that there are some fluctuations. If I look here, then the magnetizations became equal, but then there was a kind of small hump, a small deviation there, which is about of order 0.4. And this bumpiness here is due to the width of the distribution here. Okay? So because n is finite, there is a range of possible values of m, So even at equilibrium, you can find some noise. Okay, it goes up and down. So the larger n is, the smaller this noise is. So you can see these curves are a little bit noisy. If I took n to be 1,000,000, then they would get smoother. If I took n to be 1,000,000,000, they would get even smoother. Okay, so that's one observation. Another observation is about the entropy. We've got a formula for the entropy. Okay, so I made this last year where I used sigma for entropy, but sigma is the same as S, okay? It's the same thing. I just used a different symbol. So this is the entropy of the first paramagnet. This is the entropy of the second paramagnet. So the entropy of the first paramagnet goes down. The entropy of the second paramagnet goes up. But what's important is that the total entropy increases. Okay? The entropy of the first plus the entropy of the second paramagnet increases with time. And this is the statement of second law of thermodynamics. Right? The second law of thermodynamics says that these random changes in microstate should act to maximize the entropy. And you see here that that's exactly what happens. As the spin flips continue, the entropy, total entropy, is maximized. So this slide is to demonstrate the second law of thermodynamics in this example. Okay. Finally, I will say that this simulation goes beyond the theory. Right? Our theory, all of these things we've calculated, apply only in the equilibrium. Right? This is only after a long time has taken place. So what these equations are able to calculate, is the end values. Okay? Using these equations, I could tell you what is the final temperature. I can calculate that. Right? I can calculate what is the final magnetization. And I can calculate what is the final entropy. But the theory I have done is not sufficient to tell you the shape of these graphs. Okay? I can only tell you the final point. I can't tell you the shape of the graph. In order to calculate the shapes of graphs like these, you have to do non-equilibrium statistical physics. Okay? And as I said, we're not going to do that in this course. So in this course, I'm only going to be able to tell you what happens at the end. Okay. But this is a simulation which demonstrates all of the important points. The thermodynamic limit, the fact that temperatures become equal, and the fact that entropy is maximized, okay, using a statistical model. So that's a good point to finish. That's the end of our theory of the paramagnet. So from next week, we're going to go on to look at more complicated systems. And in 2 weeks' time, we're going to be able to calculate the properties of the ideal gas, which is kind of the ultimate goal of this part of the course. Okay, so that's all for now.